I, Professor Ranjana, Research Lab for Energy Systems, Department of Physics, Netaji, Subhas, University of Technology. Today, I am going to present my talk on utilization of nano microstructures of nickel sulphide for energy devices. Nowadays, with the growing population, the energy demand is increasing day by day. We have the present energy resources are fossil fuels such as coal, oil, wood, etc., but even this stock may not longer than a few decades. So, what is our future energy sources? Renewable energy sources are freely available on earth in abundant quantity and which will not finish. Thus, the energy contained by these sources in any form can be converted to the electrical energy which is essential for human. Alternative energy sources are being persuaded in many developed countries as a way to counteract the developed world's dependence on non-renewable sources that are being exhausted faster than they can be replaced. Common alternative energy sources are solar energy, wind, hydropower, geothermal energy, nuclear power, trash and hydrogen. So, why the nanostructures are utilized in energy devices? At micro scale, there are few disadvantages which are related to the energy device technologies. Limited efficiency, high manufacturing cost, less flexibility, less energy payback time and unstable for larger span of time. At nano scale, various characteristics related to the quantum mechanical effects developed due to the surface effect quantum, which is known as the quantum size effect. Quantum size effect can be different can lead to different physical and chemical properties, optical properties, tunable band gap, multiple exciton generation, enhancement of mechanical characteristics like hardness, surface activity and flexibility. So, what are the nanomaterials which we are going to use for the energy devices? A field that takes a material science based approach to nanotechnology. Materials having at least one dimension 100 nanometers or less up to the 10,000 could fit across a human hair. Nanomaterials can be nanoscale in one dimension like surface film, 2-dimension strands or fiber, 3-dimension that is particle. They can exist in single fused aggregated agglomerated forms with spherical, tubular and the irregular shapes. So, when describing the structure of a material, we make a clear distinction between its crystal structure and its microstructure. The term crystal structure is used to describe the average position of an atom within the unit cell and is completely specified by the lattice type and the fractional condition of atoms as determined by X-ray diffraction, and in other words, the crystal structure describes the appearance of the material on an atomic length scale. The term microstructure is used to describe the appearance of the material on the nanomaterial length scale. A reasonable working definition of the microstructure is the arrangement of phases and defects within the material. So, classification of the nanostructures has been shown in this particular picture, that is the 0D, 1D, 2D, 3D and the different characteristics like morphology, high aspect ratio, low aspect ratio, state and the chemical compositions, which include single constituent nanoparticles, composites, inorganic and organic, carbonaceous nanomaterial, branched quantum dots, ceramics nanomaterials, semiconductor nanomaterials, polymeric nanomaterials, nanogels, and the core shell nanomaterials. Role of nano microstructures in energy conversion and the storage devices. Energy application are of two types, that is the energy conversion and energy storage device. The types for the energy conversion which we are using: photocatalytic, hydrogen production, fuel cells, disensitized solar cells. Important structural properties are short diffusion length, large pore volume, homogeneous flow through pore structure, porous hierarchy, role of nano and microstructure in application, that is the small resistance, high storage density, high ion and the electron transportation, high current density, fast charge permeability. So, why we have chosen the metal sulphides? Metal sulphides designated as MSS, where M is Fe, Co, Ni, Cu, Mo, Ti, Ws, Sb, etc. Metal sulphides are attracting the considerable attention in a variety of energy devices due to their diverse structural types and fascinating electrochemical activities. Synthesis of metal sulphides with controlled morphologies, sizes, composites and micro and nano structures. Metal sulphides are usually semiconductors with better electrical conductivity than their oxide counterparts, which can be shown here in the particular picture. So, why we have chosen nickel sulphide? Nickel sulphide is one of the important class of metal sulphide. Nickel sulphide has unique morphology, caterpillar, cabbage, pompon, etc., high theoretical capacity, high energy density, high power density. Nickel sulphides exist in the multiple phase such as NIS, beta NIS, Ni17S6, Ni3S4, NiS2, Ni3S3, and the different phases have been shown here in this particular picture. Different phases of nickel sulphides and their structures are given here with their chemical formula, and they are NIS, Ni3S4, NiS2, and similar structure we are also finding, and the different structures have been provided in this particular table. Applications of the nickel sulphide in energy devices. Nickel sulphide used as counter electrode in solar cell, nickel sulphide used as electrode in supercapacitor, lithium ion batteries, etc. Here in this picture you are able to see the chemical, electrochemical, electric and the mechanical uses of energy which we can have in the different forms of the energy devices. So, first of all we will discuss a short introduction about the solar cell. A solar cell is a solid state electrical device that converts energy of light directly into the electricity by the photoelectric effect. A solar cell is known as the photovoltaic cell or the photochemical cell. The basic phenomenon which includes that has been picturized here. The basic structure of a photovoltaic solar cell is made of the three main parts: light absorber, carrier collector, metal contacts. Light absorber converting incident photons to electron and holes, carrier collectors capturing the carriers, that is the electrons and holes, metal contacts transferring the carriers to the circuit. So, the heart of a solar cell is the absorber layer, and the different layers have been shown here in this. This is the basic schematic of a photovoltaic solar cell. Importance of the counter electrodes in the solar cell, and they are playing a vital role. The counter electrode should be catalytic active, which reduce the over potential counter electrodes acts as a mediator or sensitizer or dye after the electron injection. Generally, researchers focused on improving the fill factor, short circuit open circuit voltage, and if the properties, that is the morphology, optical catalytic of counter electrode material enhance, fill factor of the cell increase, which is influenced by connecting in series. So, while nickel sulphides can be used as a counter electrode, and due to the unique morphology of nickel sulphide can provide more catalytic sites, high crystallinity can assure fast charge transfer. In case of sulphide, no heat treatment is required for fabrication of counter electrode. Nickel sulphide is used as counter electrode in solar cells. Nanostructures used as counter electrode. Here the JC curve of the DSSC with NIS counter electrode and the platinum plated counter electrode has been described. The same image of the NIS synthesized with the different solvents and absolute ethyl alcohol as solvent and the distilled water as the solvent, and their various properties which we have obtained, like fill factor, current density, efficiency, all has been given in this particular table which has been provided here. Nanostructures used as an electrode. The typical current voltage curves of the DSSC based upon the platinum and the NIS curve under one sun illumination, that is the 1.5 G, and the different nanostructures of the different dimensions has been shown here, which can be used, and these nanostructures of NIS can be used as a counter electrode. So, a capacitor is known as condenser, is a passive two terminal electrical component used to store in its electrical field. When a capacitor is attached across a battery, an electric field develops across the dielectric, causing positive charge plus Q to collect one plate and negative charge minus Q to collect on the other plate. So, supercapacitor is an electrochemical capacitor that has very high energy density as compared to the common capacitor, about 100 times greater. Supercapacitor is also known as the electric double layer capacitor or the ultra capacitor. The capacitor range is from the 100 farad to 5K farad. Basic designs of the electrochemical capacitors, they are also known as the supercapacitors, consist of the two electrodes separated by an ion preamble membrane and an electrolyte electrically connected with both electrodes. When the voltage is applied, ions in the electrolyte form electric double layers of opposite polarity to the electrode polarity. As for example, positive electrodes will have a layer of the negative ions and the negative electrodes will have a layer of the positive ions. These are the various structures of the capacitor, supercapacitor and the battery, which has been shown here. The construction of the supercapacitors are with the two metal foils, each coated with an electrode material such as activated carbon. The electrodes are kept apart by an ion preamble membrane, which is also known as the separator, used as an insulator to protect the electrode against the short circuit, and the construction is subsequently rolled or folded into a cylindrical or rectangular shape and is packed in an aluminum can. This has been shown here. So, nanostructures nickel sulphide, they are used as the electrode, and these are the various nanostructures with the various dimensions have been shown here. This is the FESIM image of the NIS spherical synthesized using the different sulfur contents. A schematic diagram of the assembled symmetric solid state supercapacitor device of NIS CV voltagram of the assembled device at various scan rate, galvanostatic charge and discharge curve of the device at various current densities, cycling stability test of the device at 0.26 ampere per gram. The inset shows the galvanostatic charge discharge curve of the last 10 cycles. Next, plot before and after the cycling stability test to the assembled device, and the Ragon plot all the solid state device inset showing the illumination of the LED light by our assembled supercapacitor device. Nanostructures nickel sulphide use as electrode in the supercapacitor. So, surface morphology, schematic representation of NIS based sample synthesized via in situ sulfurization approach at different time intervals, that is 1 hour, 2 hour, 5 hours, and which indicate the low magnification, high magnification and corresponding schematic respectively. Nanostructures nickel sulphide used as electrode in the supercapacitor. So, the comparative electrochemical properties of NIS based samples synthesized at different growth rate. CV inset shows the oxidation and reduction current density values for the prepared sample. GCD and C the areal capacity values with respect to the growth time NIS samples measured at a constant scan rate of the 10 millivolt per second and a current density of 4 milliampere centimeter square. Electrochemical properties of the forest like NIS, NTS, Ni foam sample synthesized at an optimal growth time of 3 hour CV and EGCD F calculated areal specific capacity versus current densities, cycling stability and schematic illustration showing the mechanism of NIS NT sample during the electrochemical process. Nanostructures of nickel sulphide they are also used as the supercapacitor. So, the electrochemical properties and the practical applicability of the hybrid supercapacitor, CV and GCD curves at different scan rates, current densities with a constant cell potential, current density versus the areal capacitance, Ragon plot real life applications of pouch cell operating a toy motor phone, LED and personal computers, cooler fans and the other energy devices have been shown here. We are using the supercapacitors. So, the battery basics, batteries produce the electricity by a spontaneous chemical reaction. Batteries convert chemical energy into electrical energy. An electrochemical cell has 3 main parts: the 2 electrodes, anode, cathode of the dissimilar method and the electrolyte. Why lithium air batteries? High specific energy density batteries are attracting growing attention as possible power source for the electrical vehicles. Lithium air batteries are the most promising system because of their higher theoretical specific energy density than conventional batteries. The lithium air battery is a metal air electrochemical cell and it works by oxidation of the lithium at the anode and reduction of oxygen at the cathode to induce a current flow. A metal air electrochemical cell is an electrochemical cell that uses an anode mode from pure metal and an external cathode of ambient air, typically with an aqueous or the aquatic electrolytes. So, nanostructures of the nickel sulphides which can be used in the as electrode in lithium air battery. The FESM image of the NIS coral like structure and the different structure. EDX result of NiCUS has been shown here, and this is showing the electrical stability curve of coral like NiS. NiS solid spheres, that product obtained after the solidification of NiS sphere at 160 degree centigrade for different duration like 0.5 hour, 2 hours, 6 hours, and the scale bars are the 200 nanometers. Here the cyclic voltammetry curves the galvanostatic charge, discharge voltage, profile specific capacitance as a function of the current density, cycling performance at a current density of 5 ampere per gram, and the saturated calomel electrodes. So, electrochemical performance of the NiS and their hybrid nanostructure. So, the samples are like nest-like hierarchical Ni3S2, it is synthesized by the hydrothermal method, Ni3S2 flakes, then 3D Ni3S2 nanosheets. It is also synthesized by the hydrothermal method. Different samples which has been mentioned here, they are being synthesized by the pulse reversal electrodeposition, hydrothermal and by the solvothermal methods. Nanostructures nickel sulphide grown in the research lab for the energy systems for the energy devices. They are the cabbage, caterpillar, pompon, sphere, womb, pyramid, nanorod, hollow sphere, nanoplates. So, key features of the nickel sulphide nanostructures which we are using for the energy device. The nanostructure cabbage, it is having the specific area 251.47 meter square. Pore dimension is of the order of 6.40 nanometer. Optical energy band is 0.98 electron volt, and it can be used as a counter electrode in solar cells. The next one, that is the caterpillar, it is having the specific area, that is the 247.45 meter square per gram. Pore diameter is of the order of 5.40 nanometer. Optical energy band gap is 0.74 electron volt, and this can be also used as a counter electrode in the solar cells. The hollow spheres, the specific area of about 300 meter square per gram, pore diameter is 8.40 nanometer, optical energy band is of the order of 0.52 electron volt, and this can also be used as a counter electrode in solar cells. This is the paper which we have published based upon these nanostructures, that is the improved electrocatalytic performance with enlarged surface area. This is the main finding, that is the enlarged surface area and the reduced band gap of the caterpillar and cabbage like nickel sulphide nanostructures. Other nanostructures like pompon, the charge transfer resistance is 2.91 ohm, aerial capacitance is 16.05 farad per centimeter square, cyclic stability is about 85%, and this can be used as electrodes in supercapacitor. The sphere, that is the charge transfer resistance is 3.91 ohm, aerial capacitance is 12.05 farad per centimeter square, cyclic stability is 83% and used as electrode in the supercapacitor. The nanorod charge transfer resistance 6.91 ohm, aerial capacitance 10.05 farad per centimeter square, and the cyclic stability is 78%, and it can be used as an electrode in the supercapacitor. The paper which we have published on these types of the nanostructures. So, there is a comparative study of the electrochemical properties of the mesoporous 1D and 3D nanostructures rhombohedral nickel sulphide in the alkaline electrolyte. And the another paper which we have published, that is the trisodium citrate assisted morphology controlled synthesis of nickel sulphide nanoparticles with enhanced cyclic stability as carbonaceous free electrode material. The another nanostructure, that is the ohm structure, the charge transfer resistance is 5.81 ohm, specific capacitance 876.56 farad, and the cyclic stability is 86%, and for the nanoplate charge transfer resistance is 6.91 ohm, specific capacitance 756.56 farad per gram, and the cyclic stability is 78%, and all of them we are using in the lithium ion batteries, simple as electrode in the batteries, both the structures, that is the pyramid and the nanoplate. Advantages of the renewable energy sources. Renewable energy sources consist of the solar, hydro, wind and the geothermal ocean biomass. The most common advantages of each is that they are the renewable and cannot be depleted. They are the clean energy as they do not pollute the air and they do not contribute to the global warming or the greenhouse effect. Since their sources are natural and the cost of the operation is reduced, and they also require the less maintenance on their plants. So, the renewable energy is our fate. Emission less, environmentally friendly, low capital investment, no running cost, easily established, less construction is required, outage of these sources less affects the system operation, and the limitations are, that is they are intermittent in nature, sustainable source of energy, but not reliable source of power. Penetration level is limited, and the higher penetration affect the stability, makes the less reliable system unpredictable with the high variability. So, I conclude my talk by giving you the brief description how we have used the NIS micro and the nanostructures for the different energy devices like batteries, solar cell, etc. We have discussed about the applications of the energy conversion and the energy storage devices. The phenomenon in which we are using, that is the photocatalytic use, hydrogen production, fuel cells, dye-sensitized solar cells, lithium sulfur batteries, lithium air batteries and the supercapacitors. For supercapacitor, both core and shell like nanostructures can be used as an active electrode because they would both contribute to enriched redox reaction which result in enhanced specific capacitance. A proper core shell combination of nanocomposites, a high surface area, desirable electrolyte transport and fast electron transfer are enabled, leading to a simultaneous enhancement in performance of the supercapacitors. For batteries, 2D shell materials can serve as a protective outer layer as well and preserve the backbone during charge and discharge cycles. 2D nano microstructure provides the mechanical strain and volume expansion of the active material generated by the fast and long time Faradic reaction can be effectively relieved due to the cross configuration and sufficient spaces, which enhance the cyclic stability of batteries. 1D nano arrays can provide a unique open network, assuring a high utilization rate of active material, which enhance the performance of solar cells. So, I am finishing my talk by a message: live green, save green. Green energy does not cost the earth. Sincere thanks to all the recording teams of NSUT studio, which is situated at Netaji Subhas University of Technology. Thanks a lot.